All right, so I'm going to record a couple of friction examples that we did in class today, Monday, November 19th, 2018. So many of you juniors were away. We're going to start with problem 28. This is chapter 5. And before we really dig in, let's just remind ourselves what we know. So we know that the force of kinetic friction on an object from a surface is equal to the coefficient of kinetic friction times the normal force on the object from that surface. So we're going to do problem 28. Let's read it. That's the first step. A 1,000 kilogram car traveling at a speed of 40 meters per second skids to a halt on wet concrete, where the coefficient of kinetic friction, mu sub k, is 0.60. Okay, so what givens do we have? We know the mass of the car is 1,000 kilograms. Let's be really clear. If we know the mass, we also know the gravitational force of the Earth on the car, which is the mass times the gravitational constant, 9.8 newtons per kilogram. So I think we end up with 9,800 newtons of weight for the car. We know that it's traveling at a speed of 40 meters per second and then it skids to a halt. So that tells me that the starting speed is 40 meters per second and it skids to a halt. So its final speed is 0 meters per second on wet concrete, where mu sub k is 0.6. And there are no units for the coefficient of friction. It's unitless. Okay, so those are the things we know. Let's just highlight them so we don't forget. We know mu sub k. We know the mass of the car. Therefore, we know the weight of the car. We know the starting speed of the car. And then we know that it brakes to a halt. All right, so those are our givens. The question asks, how long are the skid marks? How long are the skid marks? So you really want to know how far the car goes while it's stopping. That will be the skid mark length. Okay, so draw a pictorial representation. The first sketch I might draw is just what's going on with the car. So we know in the beginning it has some velocity. It's actually going pretty fast. 40 meters per second is fast. And then, so that's at the beginning. And then by the end, it's stopped. So its final speed is 0. And during this time, it is changing velocities. It's accelerating. Because it's slowing down, we know that its acceleration has to be the opposite direction from its velocity, from its motion. We know the starting and ending velocities. We don't know its acceleration. We don't know anything about time. So let's write down what we don't know. We don't know acceleration or time. Okay. So we probably need at least one of those to be able to do something with kinematics. We do suspect, because this is a kinematics variable, this is like something from constant acceleration, particle motion. We have these three equations. Remember, we have that one, we have this one, and we have the squared one. We're probably going to have to use one of these, and pretty much all of them need acceleration as an input to get something else. So we're going to need acceleration. So I'm going to write that down here. And how are we going to find acceleration? We may have to use forces. So let's see what's going on with the forces on this car. So while it's skidding, we're assuming that the driver is not also accelerating. They're not hitting the gas. So they are accelerating because they're braking, but they're not also hitting the gas. So the only forces are the normal force of the ground on the car. Let's call this thing the ground. There's the friction force between the tires and it's really the ground in the car because the tires are part of the car. And then we've got the gravitational force of the Earth on the car. So I'm pretty sure that's the most basic free body diagram we can have. We need to make sure we label our coordinate system. So the car is moving in the positive x direction. We'll pick forward as positive x. Okay, so we have our free body diagram and we have our kinematic sketch with initial and final. Let's see if we can find the acceleration using Newton's second law. Okay, so we need to write a Newton's second law equation that says the net force in the x direction is equal to the mass, this is on the car, is equal to the mass of the car times the acceleration in the x direction of the car. And we need to expand that net force equation into the actual forces that we really have. In this case, we only have one force acting on the car, that's the frictional force. And it is in the negative direction. It points opposite to our positive x-axis. So I'm going to put that in the net force side. That's the only one we have. And the mass of the car and the acceleration of the car. All right. Next, we want acceleration. We know the mass. We need to know how strong that friction force is. Remember that we have an equation for this. It's equal to the kinetic friction coefficient times the normal force of the ground on the car, and that's equal to the mass of the car times the acceleration. Now, the normal force of the ground on the car, we don't expect anything to be happening in the vertical direction. So we think that the normal force should balance the Earth's force on the car, in which case we can say that the normal force is equal to the same thing as the weight. And we know what the weight is. We already figured that out. Okay, so at this point, you could substitute in numbers to solve. I did that one using symbolic solutions. So if you're going to do this with symbolic, you would do minus mu k, mass of the car times g, divided by the mass of the car is equal to a sub x. Or you could plug in numbers. You could have minus 0.6 times 9,800 newtons equals 65 kilograms. No, that's really not right. It's 1,000, isn't it? It's not enough to be a car. Times the acceleration of the car. And if you divide both sides by 1,000, you would get 0.6 times 9.8. So I think that's going to be negative 5.88 meters per second squared is the acceleration. If I had my calculator, I'd do it the other way. These two masses cancel. Let's see. So 0.6 times 9.8 does give you negative 5.88. Okay, so that's our acceleration. So now we know this. We just figured this out. It makes sense that it's negative. And we're going to plug this into our kinematics equation to get the skid mark length. I'm just going to shrink this symbolic thing small. Okay, that's symbolic. Okay, so plug in acceleration equals minus 5.88 meters per second squared to get our displacement. And which equation makes the most sense? We still don't know the time, so I think we want to use the last one. Okay, so this first v squared, that is the final velocity. In our case, we know that the final velocity is actually 0. We know the acceleration, we know the initial velocity is 40, so we can solve for the displacement by subtracting the initial velocity from both sides and dividing by 2a on both sides, and that gives us an expression for our displacement. So we're going to have minus 40 squared divided by 2 times minus 5.88 meters per second squared, and that gives us 136 meters. So that's the answer for how long the skid marks should be. Okay, so finally, have we answered the question? How long are the skid marks? Yes, the skid marks 136 meters long. Boom. Yes. Do we have correct unit signs and significant figures? Our answer is positive, which kind of makes sense. So since positive 136 meters, car moves to the right while slowing down. That matches our sketch. Our significant figures, I'm not too fussy about that. It's 3. Is our answer reasonable? 136 meters. It's a football field. That's a little frightening, but the car was going pretty fast. Don't lock your brakes, kids. Make sure your car has anti-lock brakes. Okay, so we're good.